250,000 miles beneath the icy crust of a small moon orbiting Saturn, there is an ocean of liquid water that has never been touched by sunlight, sealed away from the rest of the universe for what may be billions of years. And every so often, that ocean sprays itself directly out into space, through towering geysers erupting from cracks in the ice, sending fine frozen droplets of its own chemistry hundreds of miles above the moon's surface. Close enough that a passing spacecraft can simply fly through the plume and catch a sample. That is exactly what NASA's Cassini spacecraft did, more than once, during its 13 years exploring Saturn and its moons. And scientists are still, right now in 2026, going back through that same data, finding new evidence buried inside it that keeps building, piece by piece, toward one of the most genuinely compelling cases for potential habitability anywhere else in our solar system. This is the story of Enceladus, the small, icy moon that keeps handing scientists exactly the ingredients life requires, and why the newest findings revealed just months ago may represent the strongest evidence yet. To understand why Enceladus commands this level of scientific attention at all, you first need to understand what Cassini actually found there, and how genuinely unusual that discovery was. Enceladus is a small, icy moon, only about 313 miles across, roughly the width of Arizona, orbiting Saturn at a considerable distance from the Sun, cold enough on its surface that liquid water should have no business existing there at all. And yet, in 2005, Cassini's cameras captured something nobody fully expected: enormous plumes of water vapor and ice particles erupting continuously from long, parallel fissures near the moon's south pole, nicknamed tiger stripes for their distinctive banded appearance. These were not simply icy vapor escaping from frozen surface deposits. Follow-up analysis confirmed these geysers were being fed directly by a genuine, liquid, global subsurface ocean, kept warm and unfrozen beneath Enceladus's icy shell by tidal heating. The constant gravitational flexing and stretching this small moon experiences as it orbits Saturn, generating enough internal friction and heat to keep an entire ocean liquid despite the moon's frigid, sunless surroundings. This discovery alone made Enceladus one of the most compelling destinations in the entire search for life beyond Earth, because it solved, in one stroke, the single biggest practical obstacle facing any search for evidence of a habitable ocean world. Europa, Jupiter's icy moon, is also believed to hide a substantial subsurface ocean beneath its own frozen shell, but that ocean sits buried under miles of solid ice, with no confirmed, continuously erupting plume offering direct access to its chemistry. Enceladus, uniquely, does the sampling work for us. Its ocean actively sprays itself into space, and any spacecraft willing to fly through that plume gets to directly analyze fresh material from a genuine alien ocean without ever needing to drill through a single inch of ice. Cassini did exactly that, repeatedly, and scientists have spent the years, since the mission ended in 2017, methodically working through that collected data, and the picture that keeps emerging is remarkable. In 2015, analysis of Cassini's measurements confirmed the presence of molecular hydrogen within the plume, a finding with real biological significance, since certain microbes here on Earth, found in similarly dark, sunless environments like deep-sea hydrothermal vents, survive by combining hydrogen with carbon dioxide to produce methane, a metabolic process called methanogenesis. Enceladus's plume contains hydrogen, carbon dioxide, and methane together, exactly the raw ingredients such a process would require, strongly suggesting the moon's ocean floor hosts genuine hydrothermal activity, chemically active vents on the seafloor, not unlike those found deep in Earth's own oceans, environments where many scientists believe life on our own planet may have originally begun. Then, in June of 2023, came a discovery that closed one of the last remaining gaps in Enceladus's habitability case. Life, as understood on Earth, depends on 6 essential chemical elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, collectively known by the shorthand KCNUPS. Cassini had already confirmed the presence of most of these elements within Enceladus's plume, but phosphorus, the rarest and generally least abundant of the 6, had remained stubbornly undetected, and some theoretical models had even suggested it might simply be scarce or entirely absent in icy ocean worlds like this one. A research team led by planetary scientist Frank Postberg at the Freie Universität Berlin went back through data collected by Cassini's Cosmic Dust Analyzer instrument and identified clear evidence of sodium phosphates, molecules combining sodium, oxygen, hydrogen, and phosphorus, embedded within several of the ice grains Cassini had sampled. The concentrations involved were not simply detectable. They were, according to the research team's own calculations, potentially between 100 and 1,000 times higher than the phosphate concentrations found in Earth's own oceans. Fabian Klenner, a researcher involved in the study, described the significance of this finding plainly, noting that determining such high phosphate concentrations readily available in Enceladus's ocean, satisfied one of the strictest requirements generally used to establish whether a celestial body might actually be habitable. The discoveries did not stop there. Later analysis of Cassini's data confirmed strong evidence for hydrogen cyanide within the plume as well, a molecule that, despite its toxicity to most complex life on Earth, plays a genuinely important role as a chemical building block in the kind of prebiotic chemistry believed to have eventually given rise to amino acids and other more complex organic molecules essential to life. Researchers analyzing this same data also identified evidence of what they described as a supercharged source of chemical energy within the ocean itself. Additional confirmation that Enceladus's subsurface sea is not simply a cold, inert body of water, but an actively energetic chemical environment, generating exactly the kind of ongoing reactions that could plausibly sustain simple biological processes over long stretches of geological time. This entire body of evidence, accumulated gradually across nearly 2 decades of continued analysis, brings us to what has actually happened most recently in the past several months, because the story of Enceladus is very much still being written using data gathered by a spacecraft that stopped operating nearly a decade ago. In October of 2025, the European Space Agency announced fresh findings from a renewed analysis of Cassini's archived data, this time focused specifically on a set of ice grains the spacecraft had sampled during an October 2008 flyby, a particularly valuable dataset because those specific grains struck Cassini's instruments at roughly 11 miles per second, a considerably faster impact speed than in many of the mission's other encounters, which allowed the spacecraft's instruments to break the material apart into more detailed chemical fragments than slower, gentler impacts typically produced. Researchers led by Nozer Khawaja at the Free University of Berlin identified an entirely new set of complex organic molecules within these fresh grains, chemical fragments containing functional groups, specific molecular structures that chemists recognize as building blocks capable of linking together into progressively larger, more complex organic compounds. This represents a clear sign that genuinely complex chemical reactions are actively occurring within Enceladus's subsurface ocean. Chemistry that, while not itself definitive proof of biology, follows exactly the kind of chemical pathway that could plausibly lead toward the more complex, potentially biologically relevant molecule's life, as we understand it, actually requires. A separate reanalysis published in December of 2025 examined a different, particularly information-rich dataset gathered from the same 2008 encounter, and confirmed the presence of organic molecules alongside detectable amounts of 5 of the 6 Knops elements, missing only sulfur in this specific batch of grains, along with clear evidence of abundant hydrogen, further reinforcing the broader picture of an ocean actively experiencing hydrothermal activity on its seafloor. And in November of 2025, an entirely separate line of research examining Cassini's heat flow measurements revealed something scientists had not fully appreciated before: evidence that Enceladus releases meaningful internal heat from both its south pole, where the visible geysers erupt, and its north pole as well, a more balanced overall heat distribution than previous models had assumed. Researchers involved in this analysis suggested that this specific balance of heat release from both poles could actually be closer to ideal conditions for sustaining a long-lived, stable subsurface ocean over geological timescales, rather than an ocean at greater risk of gradually freezing solid or becoming too energetically unstable to remain hospitable over billions of years. Taken together, a 2026 scientific review published in the journal Nature Communications describes Enceladus, in careful, measured scientific language, as an active ocean world whose plume provides unusually direct access to its own internal ocean chemistry, a description that reflects genuine scientific consensus rather than speculative enthusiasm. This is precisely the kind of language responsible scientists use when they want to convey real substantive excitement about a discovery's implications, without overstating exactly what has and has not actually been confirmed. And this is the point in the story where it becomes essential to be completely honest about exactly what all of this evidence does and does not actually demonstrate, because that honesty is exactly what separates genuine scientific progress from manufactured hype. Nothing described here constitutes direct detection of life itself, or even direct detection of a definitive biosignature, a chemical signal that could only plausibly be explained by active biological processes, rather than ordinary, non-biological chemistry. What Cassini's data has actually repeatedly confirmed is that Enceladus possesses essentially every non-biological ingredient scientists currently believe life requires: a stable, long-lived liquid water ocean, all 6 Knops elements essential to life as we understand it, a plausible ongoing source of chemical energy through hydrothermal activity, and increasingly complex organic chemistry actively occurring within that ocean over time. That is an extraordinarily compelling habitability case, quite possibly the strongest such case for any single ocean world currently known anywhere in our solar system. But habitability, the presence of the right ingredients and the right conditions for life to potentially exist, is scientifically distinct from actual confirmed biology, and researchers studying this data have been careful and consistent in maintaining that distinction throughout their published work rather than overstating their findings. It is also worth being clear about a specific point of nuance that responsible coverage of this topic has to address directly. The molecular hydrogen detected in Enceladus's plume, while consistent with the kind of chemistry that could theoretically fuel simple microbial life through methanogenesis, can also be produced through entirely non-biological, purely geochemical processes, chemical reactions between water and certain types of rock that occur without any living organism involved at all. Researchers examining this evidence have been explicit that hydrogen's presence establishes a plausible energy pathway that life could theoretically use, not proof that anything is actually using it. The same careful distinction applies to essentially every other finding described here. Organic molecules, even genuinely complex ones, form constantly throughout the universe through purely chemical processes, with no biological involvement whatsoever. And their presence, however encouraging for the broader habitability case, does not, on its own, constitute evidence of actual living organisms. Given how compelling this accumulated evidence has become, it should come as no surprise that serious mission planning is now actively underway specifically to determine whether Enceladus's ocean genuinely harbors life, rather than simply the right conditions for it. Scientific teams have been developing concepts for a dedicated future mission capable of doing considerably more than Cassini's brief. High-speed plume flybys ever allowed, potentially involving a spacecraft designed to orbit Enceladus directly, or even attempt an actual landing on its icy surface near the active plume vents, carrying instruments specifically capable of searching for genuine biosignatures, direct chemical or structural evidence that could only be reasonably explained by actual biological activity, rather than simply cataloging the kind of suggestive but ultimately ambiguous organic chemistry Cassini's more limited instruments were able to detect. Reports have indicated European space researchers are actively developing plans for exactly this kind of dedicated follow-up mission, a natural, logical next step, given everything Cassini's data has already revealed, though any such mission would still require years of additional development, and once launched, years more simply to reach Saturn and begin its work. Step back and consider the genuinely remarkable nature of this entire scientific story. Cassini stopped operating in September of 2017, deliberately plunged into Saturn's atmosphere, specifically, to avoid any risk of contaminating potentially habitable moons like Enceladus with hitchhiking microbes from Earth. And yet, nearly a decade after that final plunge, scientists are still making genuinely new discoveries from data the spacecraft gathered years earlier, applying fresh analytical techniques and asking new, more sophisticated questions of exactly the same archived measurements. Every one of the findings described in this story, the phosphates, the hydrogen cyanide, the newly identified complex organics, the balanced polar heat flow, came from data that had already been sitting in NASA's archives for years, before anyone finally recognized its full significance, a genuine demonstration of just how much scientific value remains locked inside historical spacecraft data, waiting for the right researcher, with the right question, to eventually come looking. So here is the honest, complete picture of where this genuinely significant story actually stands, right now, in the middle of 2026. Enceladus possesses a real, confirmed, long-lived subsurface ocean. That ocean contains all 6 chemical elements considered essential to life as we understand it, in concentrations that, in the case of phosphorus, dramatically exceed what is found in Earth's own oceans. It shows strong evidence of active hydrothermal chemistry on its seafloor, a plausible ongoing energy source for any potential biology, and increasingly complex organic molecules that continue accumulating in complexity with every fresh reanalysis of Cassini's archived data. What remains genuinely, honestly unknown is whether any of this chemistry has actually crossed the line into biology. And answering that specific question will very likely require an entirely new mission, one purpose, built to search directly for genuine biosignatures, rather than simply the promising chemical raw materials Cassini was fortunate enough to fly through and sample. Somewhere beneath that icy, banded surface, in an ocean that has never once seen sunlight, chemistry is actively happening right now. Chemistry that keeps looking more and more like exactly the kind of process that, here on Earth, eventually gave rise to life itself. Whether it has actually done so on Enceladus remains one of the most genuinely open and most genuinely exciting questions in all of modern planetary science. If you want to know the moment a new mission finally sets out to answer that question directly, subscribe and turn on notifications, because everything discovered so far suggests Enceladus may be the single best place in our entire solar system to actually go looking.